my name is Aleksander. I'm the author of ducktape. I also work in Scala C. I've been talking about this thing here and what can it do. So some agenda first. So first of all, I will go on a quick round about JSON APIs and how cool they are and not boring they are to produce. And then I will introduce you to ducktape. What can it do? What it really is. I will then go on to talk about ideas in CodeGen, like in general in Scala. And then we'll put all of the above together for a nice, cool example. So let's start with a story. The story is that moving JSON from socket A to socket B pays the bills like 60% of the time, at least for me. There's a really harsh truth for software development because there's a lot of like cool work to do, but there's also not so cool work to do like JSON APIs, right? But we all have to do it at some point in our lives. Yeah, and then they're also really, really mundane to create and do. So I came up with a list of things that we need to do before we like move on with our lives when we're creating a REST API. So first of all, we create the root definition with a DSL of a choice. So that's your akka HTTPs, HTTP4Ss, what else is that? I don't remember. So yeah, there's always some code to write there, right? And it's always not like really much fun to write, at least for me. But yeah. So next up is the request response model. So like probably all of your endpoints have a request model and a response model, right? Something comes in, something comes out. So yeah, so that usually takes form of case classes in Scala. You also need the additional not really boilerplate, but some things to do with actually writing up the serialization logic for that. So that's another thing. But then usually our apps have like a domain model and the API model we just created. So we also need a kind of a bridge between those two words, right? And there's some more code right there. And given that our domain models usually are not like one-to-one mappings between each other, and they also involve validation, parsing, sanitization, etc. So there's even more work to do here. But then, once we've done all of that, we should probably also document the things we just did, right? And then once we actually document it, we need to remember not to break it. So yeah, another thing to keep in mind. And then we're free to apply the business sauce. We actually can do what we came here to do. So yeah, you can see there's a lot of things going on here, a lot of things that are like prone to error at some point. So what if you actually didn't have to do all of this? What if we only had to do basically those two things? So we just document the thing we want to do, and then we do the business thing. We basically move on with our lives after that. So yeah, that's what like I will try to show you today. And the first like ingredient in all of this is ducktape. So what is ducktape? Ducktape is a micro-based library for automatic and configurable transformations. What that means for like the user is that, for example, you have a case class that has two case classes that have basically the same fields, maybe either in like the order is different, maybe one of them has more fields than the other. What that means to you is that you can just write a one-liner that basically maps between those two data models. To some of you that might sound kind of like Chimney because it is heavily inspired by Chimney. And what is Chimney? Chimney is also a Scala library for boilerplate free and type-safe data transformations. So yeah, ducktape is really a slightly different take on things first presented in Chimney. And also ducktape is a .t exclusive, so like Scala tree exclusive rather. What that means for me is I get to use all the really, really nice macro things in Scala tree and don't have to really worry about Scala 2. So yeah, I guess that's nice, at least for me. So what is it made of? It's made of type classes mainly, like one type class in particular. It's called transformer. And the transformer, like the name implies, transforms things, right? And it transforms things in a total way. Let's say so there's no way of a transformation that comes from a transformer to basically fail at runtime. Where it can fail though is at compile time, but that's completely fine for us, right? So transformer is the primitive that everything else is built out of. So there are instances for the most common transformations available out of the box. So for example, things like turning a list of ints into a vector ints, right? So maybe wrapping something into an option just by calling sum. It's all there just for you, waiting for you to use. And then there's also automatic derivation for case classes and enums. So like the meat and potatoes of the whole library, really. Yeah, let's example actually. So the first line, like just imagine that it's in every single like example I show you. So just from now on, that won't show up. So in the example, we have two sets of case classes. They're basically the same, only as I said, the field order is different. So if you want to, for example, transform between attack 1 and attack 2, attack and attack 2, with ducktape, you will just basically this. You will use the to method. And what is the to method? It's an extension method that is brought in from ducktape. And what it basically does is it materializes a transformer between those two types, so between tag and tag 2, and then immediately applies it, giving you the transformation, right? And the code that gets generated underneath looks like this. So there's no like magic things going on here. It's just a primary constructor invocation on the destination type with all of the fields basically written over from the source type. And there's also support from nested transformations, which are also not wrapped in other transformers. They're like unwrapped at compile time basically. So that's what the case class derivation does, and the rules for that is basically that when the source case class has all of the fields of the destination case class name-wise, and the types that correspond to those fields have transformer instances in scope, then the library is able to derive a transformer for you for free. There's also support for enums, like enums made of singletons. I'm actively working on supporting like proper ADTs made of not only singletons, but also other products. But for now, each only works with enums made of singletons. So another example, two enums, one of which has basically a subset of the cases of the other one, right? So we can just say this. So we can once again use the to method, and then code that comes out at the end is just this. It's just an if-else statement on the children of the source enum, and basically matched by name, and the instance from the other enum, from the destination enum, is returned as the right-hand side of the if statement. So that's what we can do like straight away. But what about the cases where some things don't perfectly line up, like they often do in the real world? So once again, we have a set of two case classes. One of which is a person, the other one is a serious person. And the only thing that differentiates them is the additional SSN field, which stands for the social security number. Doesn't really matter. So if you want to transform a person into a serious person right now, the compiler would yell at us. It will just tell us that no field name, there's no field name SSN found in person, right? So what can we do? We can use into. Into is another thing. It's basically a transformation builder of sorts. So you use into just like you would use to, only with into, right, instead of to. So then once you have your transformation builder, you can start applying the transformation configuration options, whatever, to actually fill in the blanks, right? So in this case, I fill in the blank of the SSN field. So field.const. So the first argument here picks the field from the destination type that we want to fill in. And the thing on the right is basically the constant value that will be filled in with. So there's field.const, there's field.computed, which once again picks the field and then applies a function from the source type to the destination type, to the field type of the destination field. And there's renamed, which basically allows you to take a field from the other for the other case class and just put it in, kind of like without applying other fractions. Basically a weaker version of computed in this case. Okay, so that's what we can do when like the constructors are private and available in scope. What can we do when the constructor is private, right? Because as you remember, like in that example before, you know that the automatic derivation invokes the primary constructor, but the primary constructor is not always available to us at call site. So what can you do? No, yeah, there's another example. So this basically the same set of case classes. The only change now is that serious person has a private constructor, and serious person also has a smart constructor in its companion object. So what we can do is to use via. What is via? Via takes in a method reference, let's say, that actually will use that. So that tells the library to use that method instead of the primary constructor. So in this case, it will try to fit in the fields of person into the arguments of the create method, right? So it fit in the first name, it will fit in the last name. It will fail is the SSN field, because once again, person doesn't have the SSN field. So we once again have the compiler yelling at us that no field is named SSN is found in person, right? So once again, we can create a transformation builder called via the into via method at this time with other transformation options. They're basically the same as the field ones. There's const, there's computed, and there's renamed. One thing worth pointing out is you actually get completions here due to how I believe in Scala 2 there was a feature introduced that allows IDEs to autocomplete structural types, so that's cool, I guess. So that's what you can do when the constructor is private. What about even more elaborate cases when your case classes are made of maybe other case classes that have smart constructors, or maybe are made of new types that basically don't expose public constructors but only expose smart constructors that return options, iders, etc. So once again, that's also possible. We just need to do some additional work. And the way it's possible is there's another thing called fallible transformers, which are just like transformers, only they can fail at runtime, actually. Transformer introduces a wrapper type of f, and that wrapper type is the type of basically the wrapper of the transformation. So think of it as maybe returning an option on an either. So f can be an option, can be an either, can be anything you actually want it to be. So the way fallible transformations work, they kind of work in two flavors, and those flavors are called modes in this case. So first of all, what is a mode? So a mode basically tells the automatic derivation mechanism which way of composing your fallible transformations to use. So there are two modes. There's a accumulating mode, and there's a fail fast mode. But also, modes also kind of serve as a provider of operations for those abstract wrapper types. So we need a certain set of operations to actually do the transformation with the abstract type, right? So the only abstract operations we need is basically pure, which wraps ordinary value into that wrapper type. So if f is option, then pure will just call sum on it, right? There's also the map method, which allows us to work on the values inside that wrapper type. And then we move on to the flavors of mode. So one of which is, as I said, accumulating. And accumulating introduces another method to us, the product method. And the product method takes in two values, both of which are already wrapped in a wrapper type f, which is supposed to mean that we can easily treat those two values as independent transformations, and we can run them in quote-unquote parallel mode, which will allow us to basically accumulate the errors those things produce, right? So that's how we get accumulation semantics in fallible transformations. And there's also the fail fast mode, which introduces the flatmap method. So the flatmap method takes in a value wrapped in an f and a function that goes from a to some f of b. What that means is that each fallible transformation is actually in a flatmap chain is actually dependent on the value that came before, right? So you cannot have all the transformation after a failure actually occur because they cannot exist because the call in flatmap failed. So that's how we get fail fast semantics. A quick example of that is, once again, we're back to person and serious person, this time with a twist. The serious person has a new type over the age and its field and its SSN types. So the age new type, it's not really a new type, but the age new type exposes a fallible transformer that does some validation on it. So it basically checks if the value is bigger than 0. If it's not, it gives you a nice error message. If it is, then it just wraps that in the constructor. And there's the SSN thing, new type, that doesn't expose a fallible transformer, but exposes a default value of some kind, and only exposes a smart constructor. So no fallible transformer just yet. So yeah, so to actually transform between a person and a serious person in this case, we also need to provide the transformer mode. And transformer modes need to be present at call site, not really at the call site, in the implicit scope of the call site, basically, right? For the macro to know which expansion to use. So in this case, I use the accumulating mode for iders with collection on the left side. So it can be a list, it can be a vector, it can be whatever you want. And then if I were to call person into serious person, I will also call the fallible combinator on that, which puts us into another kind of transformation builder, fallible transformation builder in this case, which we can once again fill in with our transformation options. So all of the aforementioned total transformation options are available out of the box. So const, computed, renamed, they all work here. And there are two variants on the total transformation options. So there's fallible const, which actually lets you supply a fallible value on the right-hand side. So as you remember, SSN.make returns an either of list of string or SSN. So that's what type is expected here. And fallible computed allows you to supply a fallible-like transformation from the source type to the type of that field, wrapped in the type that is actually in implicit scopes, wrapped in the type that the mode in implicit scope has. So yeah, so a call like this expands into something like this. There's a lot of code on the top that we don't really care about. The thing we care about is right here. So an accumulating transformation is actually a chain of product calls on each fallible transformation, right? So the macro would, if you have like more fields here, it will be like bigger, but of course that's a presentation. So you have a product call on the SSN.make method and on the transformer of age that we put in the companion object of age. So that was actually provided to us by the implicit search mechanism. And then that gets followed by a map call. And that map call right here, right, the structures the tuple that actually gets created during the expansion, and at the end invokes the public constructor of serious person with the values from that tuple, right? And the type that gets returned at the end is either list of string serious person. And if you were to swap out the transformation modes for fail fast this time, that will look like this. So once again, some code that we don't really care about at the top. And then the actual transformation is just a chain of flat map calls. So we get actual fail fast semantics here. Of course, with a last map call at the end. It's kind of like basically what for comprehension triggers into. So yeah, with that in mind, we can move on to IDLs. So IDLs, they stand for IDL stands for interface description language. An example of that is OpenAPI, which is a YAML-based IDL for describing REST APIs. What I'm going to talk about doesn't really concern only OpenAPI. It concerns like IDLs in general. For example, SmithyOS. But yeah, I use that as an example here. So yeah, what they are. So they're usually decorative and focused on a single thing. In the case of OpenAPI, at least, they have codegen support for every possible language under the sun. So basically, if it has a compiler, it probably has a code generator for OpenAPI for that specific IDL, or rather for OpenAPI in this case. And OpenAPI has great Scala support in the form of guardrail, and it's basically your source of truth for both implementers and consumers. So that's basically your whole documentation right here. And what goes into an IDL, and in this case, OpenAPI. So in this case, we create endpoints by basically creating some path. So in this case, I created an endpoint called /conferences that creates a new conference that has a request body of create conference. We'll look at that in a second. And it has some responses, well-defined responses. So 201 for the cases then that it all works, or 400 when there's some validation errors, basically an invalid entity. So what that will give us after the code gen step? Oh no, sorry. Also there's the object definition. So create conference is an object with 3 fields. That doesn't really matter all that much here. So yeah, let's move on. So what does this give us? It gives us the API model, right? So in case of guardrail, it will generate something like this. So all of your object definitions from OpenAPI become case classes, and all of the case classes have encoders and decoders for JSON in scope for free, code generated, right? Yeah, there's also one for date span and one from the validation errors. It also generates the unfun part, I like to call it. So the unfun part is the part where you basically create the actual definition of the root, your actual deserialization logic and serialization logic, right? So it all goes here and it's all generated for us, according to the spec we, of course, given it at the start. It also generates the response models, and at the very bottom is the actually useful part. So the handler method, it usually generates a handler method for us to basically implement, and the handler method is like a raw business logic. So only thing we need to do is we need to implement that, and we get access to the already deserialized body of the request. So in this case, create conference, right? So yeah, so once we have that in hand, so now that we know how the code is generated, we also need a way of actually structuring our domain to be as automatically transformable as possible, let's say. So yeah, so how can we do that? We can do that with new types, right? So Scala tree is nice enough that it exposes the opaque type mechanism, which basically allows us to create a new type library, quote unquote, in 10 lines of code or even less, if I didn't have to break my code like that. So yeah, in this example, I actually use refined to materialize my validations in an easy way, and then I also use source code for some nice metadata that I use in my error messages. So yeah, so there what goes into a new type in Scala tree, it is comprised of an opaque type inside. It usually has a smart constructor. So in this case, it has a smart constructor that materializes the constraint. And then I also derive a fallible transformer for that new type by just invoking the smart constructor. So nothing really fancy going on here. So yeah, the whole point of that is that for each new type we create to have a fallible transformer in scope, in implicit scope, I mean. And yeah, all the user has to do is to provide a refined type that will describe the validation. So let's get to modeling. As you remember, we're trying to model a conference, like a conference insertion thingy or something. So a conference in a domain model would look like this. So it's a case class of 3 fields. All of those fields are new types, besides datespan, I believe. So yeah, so name is a new type validated. So the thing I created on the last slide that wraps a string, and it has a validation, a constraint called unsurprising string. And an unsurprising string is just a trimmed and then an empty and a max size string of some size, right? So in this case, it's an unsurprising string of max size 20. City is basically the same. A datespan is not a new type. It has a case. It's just a case class with a private constructor that also exposes a smart constructor, right? So let's put all of the above together. So for our endpoint definition, like the one we saw before, it will look like this. So we create usually something called roots. I call it roots, right? So we create a conference roots with a conference repository. That thing is basically a stand-in for business logic, In my case, it's just basically a call to the database to create the conference. And then I extend handler of IO. IO is the effect type of my choice here. Yeah, I provide the the transformer mode I want to use. So I want accumulating transformations for my users to actually see the things they didn't do properly. Yeah, and then moving on to the actual implementation of the create conference method. So once again, we get access to the body, right? To the deserialized body, which is create conference. And like the whole point of that is to transform the create conference thingy into our domain conference thingy. So we do body into conference that's fallible because the transformation will be fallible. And then the only field that needs like a kind of help to like the only field that the library needs to help in transforming is just datespan. So we can just use fallible computed to compute a datespan by invoking the datespan that create smart constructor on it. So yeah, I then just map over the errors that I got from that transformation to actually return a bad request of a 400 thingy. And then at the very end, I actually do my business logic. So creating that in the database. So does it actually work though? So imagine I actually started a server with all the things I just wrote there, and I now try to send a request to the /conferences endpoint. I send it a JSON body with a name that has a lot over 20 chars, a datespan that is not before the end, and a city that also has a long name. And what I get is a nice like 3-element array with all of the validation errors that were caught basically. So all of that was almost automatic, because we still had some work to do, but not much, right? That's the whole point. And for a good boy request like this, so a name that is not over 20 chars, a datespan that is actually before where the start is before the end, and the city that doesn't have like too big of a name, we get a 201 like this. So yeah, so that's it, I guess. If you like ducktape, file your books, criticisms, or maybe ideas on that link. There's code samples and alternative versions that actually you submitted for us under this link. And that's all I had to say today. Thank you.
Any questions? Please repeat the question for the recording. Was the mic on this for the audience?
Okay.
Oh, are you using this?
Yeah. That's all in Scala tree. Yeah. Go ahead.
Did you hit any limitations in?
Yes, actually, like the thing, I hit some, but like they're pretty obscure, I would say. Let me just go back to the slide. So the question was, did I hit any limitation in the Scala tree metaprogramming? Let me find that real quick. Somewhere around here, I believe. So yeah, so for example, this thing at the very bottom, case X, throw match error, it's because if I just create the actual like pattern match with just the tuple at the top, right? The pattern matches generated by the macro are not exhaustive, like ever. I reported that error. It got some traction, but didn't like have a actual result like fix just yet. So yeah, so that's that was one of the errors that they caught. Of course, there were some other ones that they also reported as much, and they actually got fixed pretty quickly. But that's like the only one that's still standing. There's maybe some other ones that I didn't report because they're like really crazy to reproduce. I like couldn't get them to reproduce outside of this code base, which is not that simple anymore. So yeah, I try my best.
So you had something to accumulating.
Yeah.
Maybe you can go back to make it fast one play.
Yeah.
So when you're doing stage fast, but things when you get one.
Yes. You may. Yeah. Go ahead. Yeah, I don't. It's just that the code before was just set up to use either's basically, so that list inside will just be always like empty. And the question is, why do they use idle of list for a free hash transformation? And yeah, the answer is laziness basically.